Okay, so let's make a start. Just a reminder that you should now be working on assignment number 3. You may have noticed that there's a good chunk of time for you to complete assignment number 3. The reason for that is that it's an online exercise. I know there are technical challenges associated with getting it to work. Oh, is this not working? Can you hear me okay? At the back? Yeah, okay. So I know that there are, it's an online exercise. It uses Java in a browser. There are some compatibility issues. And so the reason that there's a big chunk of time is to give you a chance to figure out what the problem is if you can't get it to work properly. It's a great exercise. Even though there are these technical challenges, I much prefer this. I could give you the same exercise with, on a piece of paper, but it's much more informative, I think, to do it online where you can kind of drag around points and things. Once you've done the exercise, you'll understand what I'm talking about. So this is a plea to please don't leave it to the last minute. You've got lots of time to do the exercise. I forget who sent either Cheng or Avinash sent around some guidelines on how to do it, as in what browser to use, on what type of machine, it's those kinds of issues. So please do make a start if you have problems. That way you have time to figure it out with your GSI. Your GSI can help you figure out what the problem might be. Yeah, question? So you're asking the question that nobody usually asks me and everybody usually does. Yes, you can. The way the assignment works is you do the assignment, you work through the exercise, and then there's like a little test at the end. And you can do the test as many times as you like. Got a question? No, the only thing you need to hand in is that when you do the test at the end, it'll give you a certificate. You just print out the certificate that has your score on it and hand it in. Okay, any other questions? Yeah. Oh, do the activity first, otherwise you won't know the answer to the quiz. Yeah. So there's an activity, right? So it's called an activity, that's the exercise, and then there's a little quiz that you take, and at the end of the quiz, you print out the certificate. Okay? So again, please don't leave it to the last minute. You are going to experience technical difficulties, so you've been warned. Okay, so today we're going to talk about seismic gaps. And the real question I want you to have in your mind as we talk about this material, what we're going to talk about today is the distribution of seismicity, the distribution of earthquakes. And the real question that you need to be thinking about is, can we use plate tectonics to predict earthquakes? And I mean predict, of course, in the general sense of what can we use. So we have a physical model of how the solid Earth works, that's plate tectonics. And to what degree can we use that model to say something about what's going to happen in the future? That's what I mean by predict earthquakes. I don't mean predicting earthquakes that are going to occur at this particular time, on this particular day. As you all know, that is not possible. I mean to predict earthquakes in a more general sense. How far can we push this plate tectonic model to tell us about what to expect in terms of future earthquakes? Okay? And so that's what we're going to talk about today. This is kind of the beginning of us starting to ease ourselves into the final third of the class. We're actually only halfway through the semester. But if you remember the way that the class is divided up into these thirds, in the first third, it's really the motivation part of the class, where we talk about past earthquakes, the impacts of past earthquakes. We talk, of course, about the scenario earthquake. The middle third is the kind of science behind it, behind earthquake-related processes. And then the final third is what we can then do about it. How can we take this information and use it to reduce the impacts of future earthquakes? And so we're going to start to ease our way into that final third. We're going to talk today about how we can use plate tectonics to say something about where we expect future earthquakes. We're then going to talk about tsunamis and volcanoes, which are both hazards related to earthquakes, so that's why we're covering them. And then, actually, after we've done that, we take the second midterm, and then we move into the final third of the class. So again, I just want to give you a bit of sense of where we are in the class and where we're going. Okay? All right, so seismic gaps and whether we can use earthquakes as a predictor. I think this is the figure that I show the most in this class. This, of course, is the earthquake cycle that we've talked about once at length and probably mentioned 2 other times already. And so this is just to remind you that the earthquakes are the result of the release of built-up stress on faults, and that built-up stress is being created by plate tectonic processes. So we start out with a nice straight fence. This is North American plate. This is the Pacific plate's going up in this direction. The North American plate going in this direction. We build up. That strain is accommodated by deformation across the faults. You get this sort of S shape, and then you get to the point where the fault can no longer doesn't have the necessary strength to withstand this. It pops, and of course that's when we get an earthquake. Okay, so that is the earthquake cycle. It's a continuing cycle. It happens, and then we just go back to here, and we do it all over again, and we go around and around and around, and we keep having earthquakes. All right, there's no surprise that we're going to continue to have earthquakes in the same places where we've had earthquakes in the past. So looking at that earthquake cycle in a little more detail, this is showing the build-up of the crustal strain versus time. So we gradually build up crustal strain. Then we have an earthquake, so the strain drops, and then we build up again, and it drops, and we build up again. Okay? And then this is showing the same thing, but now we're showing seismicity, so there's no earthquakes. You have a big earthquake, aftershocks associated with it, so the seismicity drops down, the main shock, and the aftershocks, and so on and so forth. And so the point is that these are what we call seismic gaps. Okay? These are spaces in time when we're not having seismicity. You can think of seismic gaps both in terms of time and in terms of space. We're going to identify chunks of time and chunks of space, so along faults or along subduction zones, where there's a seismic gap, where we've not seen seismicity. That's what a seismic gap is. Okay? So this is an ongoing cycle, and so the question becomes, and so this shows it in a little more detail. This is a plot that just shows the date of earthquakes along the San Andreas fault, and this is just earthquake number 1, number 2, number 3, number 4. So this is just distributed equidistant along this horizontal axis, and it shows the date on the vertical axis. And you can see that, if this was a perfect straight line, then that would mean that the amount of time between each of these earthquakes was exactly the same. Okay? And if that was the case, then we would be able to say, on the Hayward fault, there's an earthquake every 123 years, wait for 123 years, bang, you get another earthquake. Of course, this is not a perfect straight line, right? It's wiggling around. And so it's not an exact recurrence interval. It varies somewhat. And so is this earthquake prediction becomes the question. Would you call this earthquake prediction? Somebody said yes. Why? Okay. Okay. So what he's saying is that it still has, it's not a perfect straight line, but there's obviously a trend. You could kind of draw your best fitting straight line through this, and that would tell you approximately what the recurrence interval would be, although understanding there's some kind of variability. That's right. So that's exactly right. So this tells us something. It informs us about the earthquake process. We can use this kind of data to say something about the likely recurrence interval, but we have to understand that there are these uncertainties on that recurrence interval. Okay? And so, for example, in the case of the Hayward fault, depending on which data points you use, and what I mean by that is, so this is San Andreas, but if you imagine that this was for the Hayward fault, you could go and calculate the recurrence interval of, say, the last 2 points, or the last 4 points, or the last 7 points, right? You have to choose, and of course, as you go further back in time, the information becomes more and more incomplete. So you could choose some number of points, choose all of them, and then you do your best fit line, and then you ask how much variability is there around that. That's the uncertainty. In the case of the Hayward fault, when you do that, you end up with a recurrence interval of 140 years, plus or minus, and I forget exactly, but about 30 years. Okay? So that's a big uncertainty, plus or minus 30 years. So as you know, we just passed the 140-year mark, or not just actually, 6 years ago, but there's a plus or minus 30 years uncertainty associated with it. Okay? So in a sense, you could think of this as a predictive capability, but again, it's not prediction in the specific sense that's typically used for earthquakes. It's not going to tell us that the earthquake's going to be on Wednesday at 3 p.m. Okay, so let's, oh yeah, question. This is just sequence numbers. This is just counting earthquake number 1, number 2, number 3, number 4.
So, in those kind of charts, it's just fine, like, and it's not taking into consideration, like, that photo,
Right.
place, things
Right.
like that.
Right.
Why do you even consider that?
Oh, I see. So the question was, so this is just, looking at earthquakes as a function of time. It's not talking about soils or plates or anything. Why do we call it a predictor? I mean, it's a predictor in the sense that we're not predicting what's the shaking going to be here. That's right. But that's a much more complicated problem. This is just predicting when's there going to be an earthquake on the San Andreas fault. So this is kind of boiling the problem down to the simplest possible scenario, the starting point, which is when's that earthquake going to occur on the San Andreas fault. Okay? Any other questions? Okay. So I want to sort of talk about a scenario, not a scenario, a case study, and we're going to use the North Anatolian fault for this case study. Is anybody by any chance here from Turkey? It's a long shot. I can't remember when we did the Where Are You From? Oh, no. Okay. So we're going to use the North Anatolian fault, which is in Turkey. So this is, here's a map of Turkey. And this is the North Anatolian fault that runs kind of east-west across the northern part of Turkey. And just to give you a sense, it's thought, we can think of it as being very similar to the San Andreas fault. So here's the San Andreas fault. Of course, this is California, which has been rotated just to kind of make the two faults parallel to one another. And you can see that the San Andreas fault is a similar kind of length. It's a right lateral strike-slip fault, just like the North Anatolian fault is. Okay. So these two faults are very similar to one another in terms of their geometry. And the other big difference is that we have a much longer historic record for earthquakes on the North Anatolian fault. So where we can only really talk about earthquakes in California for about the last 150 years or so, a little bit more than that, I guess. We can talk about earthquakes for the last 1,000 years along the North Anatolian fault because we have a written record of those earthquakes. All right? So that's what makes it kind of interesting. So having said we can go that far back in time, let's start with just more recent history, the 20th century. And so here's the North Anatolian fault again, okay, running across the northern part of Turkey. And each of these coloured sections shows an earthquake that occurred on the North Anatolian fault and then the date of the earthquake. Okay? And so what we can see when we look at this slip history is that there's this gradual progression. So these are, the order here is by date. And you can see that there's a progression. The first event in this sequence, 1939, was at the eastern end of the fault. 42, 43, 44, we went back and re-ruptured this piece. 57, 67. So what you can clearly see is that the earthquakes on this fault are gradually stepping their way along the North Anatolian fault, from the eastern end towards the western end. Okay? So what do you, and so the reason for this is that when one segment fails, so you release, so you imagine, think of this again just like the San Andreas fault example. So if this was the San Andreas fault, then this would be the Pacific Ocean over here, and this would be North America. Okay? And so when we talk about the Pacific plate and North American plate continually moving past one another and building up strain, well, when this section of the fault ruptured, it released the strain on this section of the plate boundary, because it did nothing for the rest of the plate boundary. So you've released the strain here, and then the strain here is released, and then the strain here is released, and the strain here is released. So it kind of makes sense that you would see the ruptures stepping their way along the fault in response to this. Okay? So what's going to happen next? So again, it went back to the eastern end. Anybody else? It will continue to build up strain. I mean, first of all, so coming back to the first comment, you can imagine that you would work your way along the sequence. Once it's done, it will go back and continue. Absolutely. Yes, it's going to continue to build up strain. The plates are moving continuously, and so the continued build up of strain is the reason it will go back and start over. What else might happen next? I'm thinking on a shorter time frame than the new sequence. Yeah. So the question was, how far west of the 67 earthquake, this is the 67 earthquake, does the fault run? Does it continue to the west? The answer is yes. So what do you think happens next? Okay. It keeps going, absolutely. In fact, that's exactly what did happen, right? So in 1999, the Izmit section of the fault ruptured. Well, we call it the Izmit earthquake because of the location of the earthquake, this dashed line. This is the town or city of Izmit, which was largely destroyed in 1999 by this earthquake. Okay. What happens next? Now we are predicting. Nothing else has happened since the Izmit earthquake. What do you think might happen next? Yeah. Exactly, an earthquake in Istanbul. So the fault continues all the way, this is the Sea of Marmara, the fault continues all the way through the Sea of Marmara and out into the Mediterranean. And the point here is that Istanbul sits right here, of course, across the, what do we call this now, the connection between the Black Sea and the Sea of Marmara. Okay, and so, needless to say, when the Izmit earthquake occurred in 1999, at the end of this sequence of events, the alarm bells went off in Istanbul, that Istanbul is next, or could be next. And Istanbul is a huge city. Izmit is a small city, a large town, and I forget the number of fatalities, but there's a very large number of fatalities, as in thousands, maybe even 10,000 in the Izmit earthquake. And Istanbul is a much larger city, and so Istanbul might well be next. And so, there was a lot of discussion about what might happen. These are photographs. This is around the time of the Izmit earthquake. You can tell, by the way, that this is what the web looked like in 1999. And so these are photos from the Izmit earthquake. But a lot of concern that Istanbul would be next. And so what should Istanbul do? So the question was, is it likely that there will be a tsunami because the fault runs through the water? Let me go back. So the fault runs right through the middle of the Sea of Marmara. So do we expect to have a... No? Why not? So the comment was, if it's too far off from the coast, probably not. That's not actually the reason. Yes. Exactly. So this is a strike-slip fault, so there's no vertical movement. So we're going to talk about tsunamis for the next week or so, so we'll talk about it in more detail. But tsunamis are generated when you have vertical motion of the seafloor. So you push the seafloor up, or you pull it down for that matter, and you either push a column of water up, or you pull a column of water down, and that's what generates the wave. Okay? This is a strike-slip fault, meaning it's horizontal motion, very little vertical motion, so it doesn't generate a tsunami. It's the same on the San Andreas fault. You don't expect an earthquake on the San Andreas fault to generate a tsunami. Great question. Yeah. Yeah, so the question was, could we have another earthquake that is in Istanbul and at the same time start over on this end? There's really no reason to think that if we had an earthquake on the next portion of the fault, that would somehow also cause an earthquake down here. So it is possible for earthquakes to trigger one another, but it usually happens in close proximity. So, so you can imagine that this earthquake here could well trigger an event very shortly thereafter along this section of the fault. Of course, that didn't happen, but that is possible. There's a physical mechanism to connect the strain. So a lot of strain is released, but it changes the stresses in this location, which can cause triggering of the next section of the fault. So you could trigger the next section of the fault. It would be a coincidence, a big coincidence, if this section of the fault then ruptured at the same time. Yeah. Why are we predicting it's going to go this way? Oh, good point. Oh, is that why you were saying it's coming back over here? I missed that. Okay, great observation. I completely missed that. So there is this little earthquake over here, 1992, okay, that occurred before the 1999 earthquake, but after the 1967. I completely missed that. Right? So that was the reason that she was suggesting that the sequence has already started over again and might expect it to be here next. So that's a good point. So the point is that the strain is continuing to build up at this end of the fault. So we may well be the beginning of another sequence started in 1992 and will continue over here. That's right. However, it's a much longer history since there was any rupture on the fault over here. So still, I would say that this section of the fault is the one that we should be most concerned about. Okay? What also is concerning about this, of course, is that Istanbul is at risk from that earthquake, which has a huge population associated with it. Okay, so back to my question. So if you were a resident of Istanbul, and this is the week after the 1999 Izmit earthquake, you've just seen, I wish I could remember the number, but maybe tens of thousands of people killed in Izmit in that 1999 earthquake. What would you do? What should the residents of Istanbul do? Not a rhetorical question. Yeah. Have earthquake kits. See, the message is getting across. Have earthquake kits, have water. So sure. So an emergency, so what more motivation could you possibly think of to have your earthquake plan? That's right. What else? Yeah. Right. So you can see, hopefully you can kind of make out in this picture from Izmit. This gives you a sense of the buildings in Izmit, and of course it's very similar to the buildings in Istanbul. So one of the things that was really obvious in this earthquake is a lot of the mosques survived. Okay? The mosques typically were much older buildings built with basically most of them were built with very large stones that are basically stacked on top of one another. And all of this here, you can see these are all collapsed, more recent concrete-type construction. Not all of them collapsed, of course. Here's probably a resident, an apartment building that didn't collapse. But you see a lot of these sort of pancaking of apartment buildings like this. Here you go, another great example. And actually some of the more historic buildings, like that mosque, survived the earthquake. So the comment was, we should implement building codes. In fact, at the time of the Izmit earthquake, Turkey had building codes very similar to California's. The problem was that they were not being enforced. So this was one of the things that became very clear after the Izmit earthquake, was while these building codes were in place, they were not being enforced. And one of the outcomes was that builders were using much a higher ratio of sand to cement in these buildings. So the concrete buildings were actually quite a bit weaker than they were supposed to be. And that's part of the reason for the collapse. So yeah, so the immediate thing you can do, of course, is to have your plan, have your kit. The longer-term solution, of course, comes from the buildings. But therein also lies the problem. Izmit is a historic city. There are thousands and thousands of buildings that are more than 100 years old. And there's nobody who's going to go back and knock down all of these buildings and rebuild them. So yes, any new buildings can be built to modern standards, and in theory, at least they are. But we're still left with the historic building problem. And the vast majority of people who live in Izmit live in these old buildings that have a high likelihood of collapse in an earthquake. So this is a real problem, right? This is a real dilemma. There is no simple solution. Yeah, question?
Oh, do you mind turning off your mic?
Oh, can you not hear me very well? Can anybody else not hear me very well? So it is turned up. Is that better? Oh, yeah, sounds better. Okay. Okay, so this is the real dilemma that exists for people in Istanbul. But this is not the first earthquake sequence. So we've just been talking about this earthquake sequence that worked its way along from the western end to the eastern end. This is sort of a previous sequence. You can see that the dates are sort of all over the place a little bit. There's a very early event here, but then it sort of looks like there's a progression going in this direction, and then an even earlier sequence from 967 to 1050 AD going in this direction. Istanbul, of course, used to be called Constantinople, and there are many historic records about large portions of Constantinople being destroyed in past earthquakes. So this is a cycle that continues. There is no simple quick fix. You can't just fix the entire city, and so this is something that the city itself continues to struggle with. What would be interesting would be to know whether the enforcement of the building codes has really improved after the Izmit earthquake. At this point, sort of whatever that is, 8 years after that earthquake, whether those building codes are still being enforced. Yeah? What do you mean? Okay. So the question is whether it's possible for the cycle to start over at the eastern end and continue going along at the western end, and the answer is yes. So I like this. Seismologists like this example because you see this progression along the fault. But don't get too focused on that. I'm going to show you other examples that show you that this approach does not work. Okay? So the point here, I'll give you the bottom line, is that we could have an earthquake on any section of active faults at any time. And just relying on seeing these kinds of sequences to decide whether you're next or not, that is not the right approach to take. So to demonstrate that point, let's come back to California and the San Andreas fault. So back in 1988, there was a huge amount of excitement because seismologists thought they had figured out how to predict an earthquake. All right? Turned out they were wrong, to be very clear, but there was a huge amount of excitement about this. And so they were looking at this exact same principle of trying to look for a sequence of events on faults, understanding the recurrence interval, identifying where there was a gap, i.e. where we were expecting an event, and then saying that was the place where we had high likelihood of an earthquake. So back in 1988, the USGS, and it's not just the USGS, it's the seismology community as a whole, put out this map showing the likelihood of earthquakes. And so the likelihood, this is the chance of occurrence of an earthquake in percent in a 30-year time period. So the higher the bar along the San Andreas fault, the more likely it is that they were expecting it to be a big earthquake. And then the color shows the reliability of the prediction. Okay, so not very reliable is blue, then yellow, then orange, then red. Okay, so they put out this earthquake forecast in 1988. Okay, and so this actually has been modified after that. But then in 1989, the Loma Prieta earthquake occurred. And the Loma Prieta earthquake, of course, occurred on this section of the San Andreas fault. Okay, so here's a map of the seismicity along the San Andreas fault. This is now looking sideways on at the fault plane like we normally do. Along the San Andreas fault is shown up here. This is what we call the creeping section of the fault. We haven't really